Have you ever gazed at the stars and wondered just how far away they are? This question, seemingly simple yet profoundly complex, can lead us down a winding path of scientific discovery and philosophical contemplation. As we look up into the night sky, we are met with the vast expanse of the cosmos, an infinite celestial wilderness that stretches far beyond our earthly realm. This boundless wilderness is populated with an array of celestial bodies, galaxies, nebulae, black holes, and more, each shrouded in mystique, each holding its set of enigma. One of the most compelling mysteries that our universe holds is its sheer size. The magnitude of the cosmos is so colossal that it often defies human comprehension. We're talking about distances so vast that they are measured not in miles or kilometers, but in light years, a unit so large that it boggles the mind. Understanding these astronomical distances is both an engineering challenge and a matter of sheer scientific curiosity. The tools we need to grasp these vast expanses cannot be found toolbox. We can't simply stretch a giant tape measure from one point in space to another. Instead, we must rely on a plethora of scientific disciplines including physics, mathematics, and even a fair share of creativity to devise complex methods of measurement. Each celestial body that we observe has its own distinct cosmic address, a unique position in space that needs to be accurately calculated, measured, and mapped. To determine these cosmic addresses, we need more than just a basic grasp of geometry. We need a deep understanding of concepts, gravity, time, and space. Our quest to understand the universe is akin to a cosmic dance, a complex choreography of numbers, formulas, and theories, each contributing to comprehension of our place in the cosmos. The journey into understanding these astronomical distances is not just an intellectual pursuit or a mere trivia fact, it holds profound implications for our understanding of the universe, its evolution, and our unique place within it. It allows us to delve into the life cycle of stars, the formation of galaxies, and the birth of planets. It can even give us insights into the origins of life itself, offering potential clues about how and where life might have originated. The sheer enormity of the universe, with its galaxies and infinite expanse, can often seem overwhelming. It is a testament to human curiosity, tenacity, and ingenuity that we have been able to devise ways of measuring and understanding these astronomical distances. Despite the mind-boggling complexity of the task, we continue to push the boundaries of our knowledge and our capabilities. The sheer scale of the universe can be mind-boggling, but our methods of measurement are even more fascinating. As our journey of cosmic discovery continues, we stand on the precipice of deeper understanding, equipped with the tools, the knowledge, and the relentless curiosity to continue exploring the infinite depths of our universe. The first method to understand is the Astronomical Unit, or AU. The Astronomical Unit is a unit of measure that we use in astronomy to describe enormous distances in the cosmos. Picture it as the cosmic yardstick, if you will. But what exactly is it based on? Well, the astronomical unit is defined as the average distance from the Earth to the Sun. That's approximately 93 million miles or 150 million kilometers if you prefer the metric system. Now, why do we use the astronomical unit? Simply put, it gives us a baseline, a starting point for measuring the vast distances in our solar system. Imagine trying to describe the distance between your house and the nearest grocery store in terms of inches or centimeters. It would be an absurdly large number that's not very useful or easy to comprehend. That's why we use units like miles or kilometers for such distances, and the same principle applies in space. When we're talking about distances within our solar system, it's far more practical to use astronomical units. For example, Mars is roughly 1.5 astronomical units from the Sun. That means it's about 1.5 times the average distance from the Earth to the Sun. On the other hand, Neptune is about 30 astronomical units from the Sun, which is 30 times the Earth-Sun distance. However, while the astronomical unit is incredibly useful for measuring distances within our solar system, it falls short when we start considering the vastness of the universe beyond. For those immense distances, we need to use other measures, which we'll discuss in the next scenes. One last thing to remember about the astronomical unit: it's not a fixed measure, but an average. The Earth's orbit around the Sun isn't a perfect circle, but an ellipse. This means our distance from the Sun varies throughout the year, and the astronomical unit represents the mean distance. So when we talk about distances in our solar system, we often use astronomical units as our yardstick. Beyond our solar system, we need to use much larger units of measurement like light years and parsecs. Imagine for a moment that you're on a road trip across the cosmos. Instead of miles or kilometers, you're tracking your journey in terms of light years. This isn't just a fanciful exercise but a very real aspect of astronomical science. A light year is the distance light travels in a year, cruising along at a speed of about 186,000 miles per second. In a single year, light will journey about 6 trillion miles. That's a 6 with 12 zeros behind it, a figure so large it boggles the mind. Now let's talk about parsecs. No, it's not a unit of measurement from a science fiction movie, but a very real, very large unit of distance used in astronomy. A parsec is equivalent to approximately 3.26 light years. The name parsec is a portmanteau of parallax and second, and it refers to the smallest angle an object can move to appear in a different position to an observer. It's a bit of a complex idea, but it's all about perspective. So why do we use these enormous units of distance? Simply put, space is vast. It's so large that using miles or kilometers to measure distances between stars and galaxies would be impractical. Imagine trying to tell someone that a certain galaxy is trillions upon trillions of miles away. It's a number so large it would be nearly impossible to comprehend. But when we say that a star is, say, 10 light years away, or a galaxy is a few thousand parsecs distant, it gives us a better handle on the sheer scope of the universe. These measurements, light years and parsecs, allow us to comprehend the unimaginable distances between stars and galaxies. In essence, light years and parsecs are the cosmic yardsticks by which we measure the universe. They're our way of mapping the cosmos, of making sense of the vast and awe-inspiring distances that separate the stars and galaxies. These measurements, light years and parsecs, allow us to comprehend the unimaginable distances between stars and galaxies. For even greater distances, scientists use a phenomenon called redshift. Picture this: you're watching a fire engine race down the road with its siren blaring. As it speeds away from you, the pitch of the siren seems to change, becoming lower. This is an example of the Doppler effect, where a change in frequency happens because of the relative motion between the observer and the source of the sound. Redshift is the cosmic version of this Doppler effect, but with light instead of sound. Now let's imagine a galaxy racing away from us at a significant fraction of the speed of light. The light that this galaxy emits shifts towards the red end of the light spectrum. This is because as the galaxy moves away, the waves of light get stretched. This stretching of light waves results in a shift towards the longer, redder wavelengths, hence the term redshift. But how does this help us measure distance? Well, the degree of redshift in a galaxy's light reveals its speed relative to us. And here's where things get exciting. The farther away a galaxy is, the faster it appears to be receding from us. This is a key evidence of an expanding universe. The universe isn't just sitting static, it's continuously growing, with galaxies moving away from each other. By observing the degree of redshift, astronomers can calculate a galaxy's recessional velocity, essentially how fast it's moving away. And because of the correlation between distance and recessional velocity, they can then estimate the distance to that galaxy. Redshift isn't just a tool for distance measurement, it also provides us with a glimpse into the history of the universe. Since light takes time to reach us, observing distant galaxies is like looking back in time. The farther a galaxy is, the older the light we are observing. Thanks to redshift, we can gauge the distances to the farthest reaches of the observable universe. It's a fascinating method that combines physics, astronomy, and a bit of detective work to unlock the secrets of our vast and ever-expanding cosmos. Space is vast, and measuring its distances is no easy task. We've traveled a long way today exploring the cosmic yardsticks that help us make sense of the universe's enormity. We started with the Astronomical Unit, our first step, which uses the average Earth-Sun distance as a base measure. From there we ventured further with light years and parsecs, allowing us to comprehend the vastness of galaxies beyond our own. And then, we delved into the intricate world of the Redshift Method, a tool that allows us to measure the distance of far-off galaxies, providing a glimpse into the universe's past. Each of these methods, from the Astronomical Unit to the Redshift Method, plays a crucial role in our understanding of the universe. They not only measure distances, but also help us unravel the mysteries of the cosmos. Next time when you look up at the stars, remember, you're not just seeing lights in the sky, but a complex map of distances that took centuries to understand.